curious minds, welcome back to ProjexCellence ProDigy, your one-stop solution for project management and mechanical engineering concepts. I am Govind, a certified PMP and mechanical engineering professional. If you drive a car, if you ride a bike, you are already using thermodynamic cycles every single day. In the next 3 lessons, we will explore the working cycles of reciprocating internal combustion engines, the Otto cycle, the diesel cycle, and the dual cycle. These cycles form the foundation of how engines convert fuel into useful work. But to build a strong understanding, we will take them one by one. So in today's lesson, we will focus on the Otto cycle, the fundamental working principle of petrol engines. The Otto cycle is an ideal air standard thermodynamic cycle which is named after Nicholas Otto. He was a German engineer who invented the first practical internal combustion engine using the 4-stroke cycle, now known as the Otto cycle. It represents the working principle of petrol engines, gas engines, and many light oil engines. Now here is one question. Why do we study the Otto cycle as an ideal air standard cycle when real engines use petrol-air mixture? Because real engines are very complex systems. Inside an actual engine, fuel and air are mixing, combustion is happening, heat is being lost, friction is present, gas composition is continuously changing. So analyzing this directly becomes very difficult. That's why engineers use something called air standard assumptions. We simplify the system by assuming only air is present, no chemical reaction. Air behaves as an ideal gas and processes are perfectly reversible. This helps us understand the engine without complications. So, the ideal Otto cycle becomes a reference model. Let's understand the processes. First process 0 to 1, intake stroke. If you observe here in the PV diagram, this segment represents the intake process 0 to 1. The piston moves from top dead center to bottom dead center. Fresh charge enters the cylinder. Pressure remains almost constant. You can see here in the graph. Second process is compression 1 to 2. The piston moves upward BDC to TDC and volume decreases. You can see here. Pressure and temperature increases. This process 1 to 2 is isentropic compression, which means entropy remains constant during the process. In isentropic, we combine two ideal assumptions, adiabatic and reversible. Adiabatic means no heat enters or leaves the system. All the work done on the gas goes into increasing its internal energy. And reversible means perfect process. No energy losses, no friction, no turbulence, slow and perfectly controlled process. Now comes the most critical moment, combustion, process 2 to 3. Here, at TDC, spark plug ignites the mixture and heat is added at constant volume. We can see here. And pressure shoots to maximum and temperature rises sharply. After combustion, the gas inside the cylinder has very high pressure and high temperature. Now this high energy gas pushes the piston downward from TDC to BDC. This process 3 to 4 called the power stroke, and this is the only stroke that produces useful work. Here, as piston moves down, the volume increases. We can see here, and gas expands. And according to gas laws, when volume increases, the pressure decreases. So during expansion, gas does work on the piston. Energy is used to push piston down, rotate crankshaft. So internal energy decreases and temperature also decreases. This process also assumed isentropic. No heat loss to surroundings. Entire energy is converted into useful work. Entropy remains constant. Near the end of the power stroke, the piston is close to BDC. Pressure inside cylinder is still high and exhaust valve opens suddenly. Now at this moment, the gas inside cylinder has high pressure and there is low pressure zone in exhaust manifold. So gases rush out rapidly. This is called blowdown, process 4 to 5. Very fast process. Gas escapes due to pressure difference and cylinder pressure drops sharply. In ideal cycle, we call it as constant volume heat rejection. Finally, exhaust stroke 5 to 0. After blowdown, most of the high pressure gases have already escaped and cylinder pressure is now close to atmospheric. We can see here 5 to 0. The piston now travels from BDC to TDC and this upward motion pushes out the remaining exhaust gases. Think of it like clearing the cylinder for the next fresh charge. At the end of this stroke, piston reaches TDC. Exhaust gases are mostly removed. Then exhaust valves close and intake valves open and fresh charge enters and new cycle begins. So in 4-stroke engine, the complete cycle consists of 4 stages: intake, compression, power, exhaust. Each stroke requires 180 degree of crankshaft rotation. So when we calculate the total, 4 stroke into 180 will be 720 degree. That means the crankshaft completes 2 full revolutions for 1 complete cycle. And here is the key point. Out of these 4 strokes, only one is the power stroke, the stage where useful work is actually produced. So effectively, 1 power stroke occurs for every 2 revolutions of the crankshaft. Now let's understand something even more powerful: the temperature entropy diagram of the Otto cycle. If you see this graph here, vertical axis is temperature and the horizontal axis is entropy. We denote it with S. During process 1 to 2, as this is the isentropic compression, entropy remains constant. We can see here, and temperature increases. During process 2 to 3, heat is added at constant volume. Temperature rises sharply and entropy also increases. During process 3 to 4, this is isentropic expansion, no heat transfer, entropy remains constant and temperature decreases. During process 4 to 1, heat is rejected, so temperature decreases and entropy also decreases. If you observe carefully, the area under 2 to 3, here, this complete area, is heat supplied, and the area under 4 to 1, here, this area, is heat rejected, and the area enclosed by the cycle represents net work output of the engine. So while the PV diagram shows pressure and work, the TS diagram clearly shows heat transfer and efficiency. If you truly understand the TS diagram, you understand the thermodynamics of the engine. Thermal efficiency of Otto cycle. Thermal efficiency is defined as work output divided by heat supplied. Means heat supplied minus heat rejected divided by heat supplied. Heat is added during process 2 to 3 here, and heat is rejected during process 4 to 1 here, and both processes occur at constant volume. Since these are constant volume processes, so we will use the formula Q is equal to mCV delta T. So we can write during process 2 to 3 heat supplied Qs is equal to mCV T3 minus T2, T3 minus T2, and heat rejected QR is mCV T4 minus T1, T4 minus T1. So if we put this Qs and QR values here in this formula, so it will be mcb T3 minus T2 minus mcb T4 minus T1 whole divided by mcb T3 minus T2. So after simplifying it further, we will get the efficiency of Otto cycle is 1 minus T4 minus T1 whole divided by T3 minus T2. If we take T1 out of bracket in numerator and T2 out of bracket in denominator, so equation will look like this. 1 minus T1 T4 by T1 minus 1 whole divide T2 T3 by T2 minus 1. So this is our equation 1. So we will simplify it further. We know that process 1 to 2 and 3 to 4 are isentropic processes. So the equation for isentropic process is Tv raised to power gamma minus 1 is equal to constant, where gamma is equal to Cp by Cv. Cp is specific heat at constant pressure and Cv is specific heat at constant volume. Gamma tells us how much more heat is required when gas is heated at constant pressure compared to constant volume. So applying this relation for process 1 to 2, we will get the equation T2 divided by T1 is equal to V1 divided by V2 whole raised to power gamma minus 1. Similarly, for process 3 to 4, the equation will be T3 divided by T4 is equal to V4 divided by V3 whole raised to power gamma minus 1. Here we know volume ratios V1 by V2 and V4 by V3 are equal to the compression ratio, small r, V1 by V2. Why? V1 is the total volume in this graph, total cylinder volume, and V2 is the clearance volume. And similarly here, V4 is representing total volume and V3 is clearance volume. So total volume divided by clearance volume is compression ratio, small r. So here we can replace T2 by T1 is equal to T3 by T4 will become R raised to power gamma minus 1. And if we rearrange this equation, so it will be T4 by T1 is equal to T3 by T2. This equation we had from our last slide. And here we have proved T4 by T1 is equal to T3 by T2. So this become equal to this. So we can cancel it out. So the efficiency become 1 minus T1 divided by T2. And from here we can replace T1 divided by T2 as 1 minus 1 divided by R raised to power gamma minus 1. So this is the final formula of thermal efficiency of Otto cycle. This simple equation tells us something very powerful. When the compression ratio increases, the temperature rise during compression is higher and more energy is converted into useful work during expansion. So therefore, efficiency increases. This is why engine designer aim to increase compression ratio. However, in petrol engines, there is a limitation. The fuel-air mixture is compressed before ignition. If compression ratio becomes too high, temperature becomes very high. Pressure increases significantly. And this can cause auto ignition before the spark, which is known as knocking or detonation. This formula helps engineers decide what compression ratio to use, how to balance efficiency and safety. So it directly influences real engine design. Another benefit, if you know the compression ratio, you can estimate engine efficiency without physically testing it. And this saves time, cost and effort in design and analysis. As we discussed earlier, the Otto cycle represents an ideal engine with no losses. But in a real engine, heat is lost to surroundings and friction reduces useful output. Combustion is not perfectly efficient. By comparing ideal and real performance, engineers can clearly identify where energy is being lost. So, to conclude today's lesson, the Otto cycle shows how engines turn heat into useful work. Only one stroke gives power, but all four strokes are needed. It helps us understand real engine performance and losses. In next lesson, we will discuss about diesel cycle. If you found this useful, like, share and subscribe to ProjexCellence ProDigy. Namaste, goodbye, Sampai Jumpa.